want to do that? That's how low pressure you do.
Oh, wait, this is what London is like. Everyone there jumps a lot. Picture, you have to jump like this. Like, I don't know if I can jump that much. You're gonna have to turn down to
Do
that.
they have like heated floors?
Yeah, the floor is lava.
Ages of social. See everyone, no one's walking anywhere. Yeah, the jump cutters.
So how's homework 3 coming along? Neural networks? Anybody has done everything? The likelihood one. I think we posted the derivation, right, on Piazza. Yeah, the wide data set, we split it for you in training and testing. The TAs have those files. I'm going to post them online on the homework today. I mean, if you did it by yourself, like you chop off a 10% or 15% set, that's fine too, but we like to run it on the one we have so that we don't get lucky or unlucky results depending on the split. The data set is very small so that you can debug a network on your laptop. I'm going to add a non-credit exercise that asks to run the neural network, the likelihood one, on a more difficult data set or larger data set, to the point where I think most people, if they implement it correctly, can run it on their laptops. But if you don't implement it correctly or not efficiently, it may not be possible to run it on a laptop. But that's not for points. That's not for grades. So if you have the wide data set running and the autoencoder, that's that. By the way, that problem is hard. The square problem, hard. We'll talk about it this week. Okay, so where are we? We're moving on from neural networks to generative methods, which we started last time. So that's probability. So what we're going to have here is a quick recap. Y is the label or the class. So what we want to do, class could be, for example, 0, 1, right? Or minus 1, 1. Or it could be red, blue, green, yellow. Or it could be categories like sports, politics, entertainment. That's what the class means. So what we're going to do here, we're going to say we want to build a probabilistic model for each class value. In other words, we're building a probability that says who's P of X in a specific class, Y equals say red. That means effectively the same as building probability of X given Y red. Because I'm building a model only for the red data points, or only for the one data points. So I'm building for each class its own model. And then a model, it's, we should say, with parameters, right? So I'm going to build a model by saying I'm going to assume the data comes from some nice mathematical function like the Gaussian function. That's what we're going to have for the homework. And we say build a model means what? Find best parameters. Build, that's what it means. Because we already say the data is Gaussian. And I'm looking at the data separately for class 1, for class 0, or red, or blue, politics, right? Each one of these gets its own model. So now I have this model that says what is the chance of seeing a data point X given the label red. That is what's the chance of seeing a patient like the one I'm seeing, a particular patient, given that this patient is sick? Or what's the chance of seeing that sort of email, given that the email is not a spam? And then what happens when I get at the test phase? So that's kind of the train mode. And at the test, I get the point X, right? Some data point X. What do I do with it? What I need to do is to compute the probability of Y given red given X, probability of Y given blue given X, all the classes. This is the class probabilities. Probability of Y given, say, K or Y. And then take R max. Or some softmax, or some other way to say, okay, given these properties per class, how do you make the final decision, right? Typically, you take the highest probability and say, that's my prediction, right? But there's some mathematical mechanism to do that properly. We're not worried about that right now. Now, who is this? How do I compute those things given what I build? I apply the base formula, right? So I say probability of Y given red equal X is probability of X given Y red, right? We discussed this, that base formula works even if X it's a multivariate. X it's all the features, right? So if the data has 50 features, this is 50 X1, X2 up to X50 times, how was the base formula? Y equal red divided by? And what happens for the blue? Probability of X given Y blue times probability of Y blue divided by probability of X. So we made several observations about this, twice already. This is the third time. Number one, this it's a prior from data. So probability of this independent of X is like how many people are sick in general. How many spams are emails are spammed in general without looking at a particular email. This is very easy to estimate from data. I look at my training set and I say what proportion of my training set is red. So this is a prior. We also made the observation that this is a normalization. Can be obtained by marginalization. We did this last time. It's effectively take all the possible numerators and sum them up, right? You take this numerator, that numerator, so on and so forth. This denominator has to be their sum if you want those values to sum to 1, right? If I have another one here, right? Probability of X, Y equal green times probability of Y equal green divided by P of X. If those are all my classes, right? Let's say 3 classes here. This has to be a distribution, right? I mean, the chance for any patient having red or blue or green, those numbers have to sum to 1, because it's gotta be one of them. We're all on the same page here. So how can they sum to 1? The only way to sum to 1 if the denominator is the sum of the 3 numerators. This is what we did last time, right? We show that if you want to marginalize X out of the joint P of XY, is the sum. So I have a joint P of XY to random variables. Right? And what we did last time is to show, well, you sum over all values of Y over P of X, this is Y value, and Y equal that value, right? Which is the sum of all Y values of who? P of Y value times probability of X given Y is Y value, right? That's the marginalization process. It's the same like we did a week before when we look at that table and say, if you want to marginalize X, you want to sum up the joint for that column or row, depending how you want to marginalize. That's the sum right here. And this is the decomposition of if you want two things to happen, you need one of them to happen first, and then the other one, the conditional, even that the first one happened. You guys remember all that? So in probabilities model in machine learning intro class, the most difficult part is not the actual calculations of probabilities. There are some really tricky things that TAs have to help you with covariance matrices and inversions, because of that if you do it naively, you get a bad result. It's a very unstable operations. But other than that, it's the setup of these conditionals and joints that's gonna throw you off. And interesting books, the Kevin Murphy book or the Bishop book, the books that are worth reading machine learning books, are too advanced for beginners. So that's why we don't use a textbook in this class, because those books would be too difficult. And the easy books are useless. They're not, I mean, it's better to just use my notes. But those books, the difficulty in them is not like you don't get how the calculation goes. That's easy. In both those books, which are very, very good books, Bishop book and Murphy book, if you could read those, that would be amazing by the time you graduate. But probably you need some more probabilities in machine learning to read. The difficulty in there is keeping track of who's who in those they both probabilities-based books. So both of them have a lot of probabilities in them. And it's hard to keep track when you read them. Okay, who was P of X? Who was P of Y? Is that a joint variable? Is that a conditional? That's the hardest part when you read those books. That's why I'm insisting on the setup. At all points, we have to know who's X, who's Y, what do we mean by X given Y, why do we Y given X, so on and so forth. All right, so we established that this is a marginalization, and if what we want is R max, then what?
Doesn't matter which we divide by.
We don't really need P of X if we want R max. We just pick the biggest numerator, that's the R max. Now if we want an actual probability, say I don't just know which one is it, I want to know it's 80%, 60%, 75%, then I have to find the right P of X and normalize it to get that normalized value. Those would be fake probabilities. Every time we build these models, those are not actual natural probabilities. It's whatever comes for my assumption with parameters. I'm assuming the data is Gaussian, so I'm computing probability based on the Gaussian, but patients in reality are not really Gaussian distributed, maybe, or images or spam emails, right? So I can compute fake probabilities, but it doesn't mean, even if I produce a normalized value here, 0.75, it doesn't mean the chance is truly 0.75. There's an entire field that I talked about calibration, those things. How do you take a bunch of scores and a validation data set to make sure your probabilities actually match reality? That's a different thing.
So the last time you said that it is a difficult problem to really calculate px, the denominator. There is a lot of research on it. But now, easily through marginalization, we calculated it. How is it a difficult problem if you're able to calculate it using marginalization?
No, so it's not difficult if you could do this, but what if I have many, many classes, right? In some problems I have 2,000 classes or 3,000 classes, and I don't even want to compute all of them. Some of them, if they have small probability, I just want to know they have negligible, like easy, small probability and ignore them. In some problems, it's a computational issue to run all of those exact probabilities being so small, especially if I have many classes. I run into computational stability problems, like they are too small. And sometimes my models make them even smaller than they are. Sometimes if I multiply probabilities, I get small numbers very, very quickly. Right? So if we need P of X, sure, that's the way to do it, and it's going to be easy for any homework, anything that has 3 classes, 4 classes, that's you compute those probabilities, and then you get P of X at their sum. Sure. What I was saying is that I think there's one thing to compute it based on a model. Models usually work for things that have enough data. So I want to fit a Gaussian, assuming the data is somewhat Gaussian. If I have enough data points in that class, right? Because it's a one model per class. Suppose the red class has enough data points. I could fit the Gaussian well, that model. Now, sometimes, very often, if you have many classes, some of those classes have very little data. When I have very little data, my probabilities are weak estimated, they're not correct. And then based on those properties, I get all kind of weird results. So in practice, to estimate this P of X exact comes down to what's the chance of seeing, in English, what's the chance of seeing a patient like Virgil? Well, if Virgil is a typical patient, I can compute that pretty well. I can estimate it well, because I've seen a lot of people like this. But if I see a patient that has some sort of anomaly, like some sort of rare disease or rare combination of blood with disease, with age, and with location, it's going to be very hard to estimate this if I have very little data. There's only one guy like that, right? So in practice, it comes down to the old problem of if I see something that's very rare, what's the probability of seeing? I know it's small, but it's hard to tell exact how small it is. All right. Same thing is with emails, right? Every once in a while, I get a weird email that's hard to classify like as a typical spam or typical not spam or something like this. Good. So we have a plan here. When we did last time, we did naive Bayes, which naive Bayes says, I'm going to try to do this. This is the plan for predictions, but I'm not going to use building a model. So in naive Bayes, we make a different assumption. So this is a shape assumption here. So I could do the same. This part, the testing part, can do. I have an alternative here. Right, so that's a shape assumption. The other one is an independence assumption. That says probability of X given a Y class is probability of X1, X2, XD given Y class. Still, I'm building a model for each class. So that part I'm doing the same for each class, right? But not with the shape assumption or with the independence assumption. I'm going to say that's probability of X1 given Y times probability of X2 given Y, probability of XD given Y. So now I don't have to fit parameters in here. I mean, I could if I want to, but typically I can estimate this by counting. So probability of Xi given Y is estimated from data via counting. What do I mean? Xi is a particular feature. It's one feature. It's the, say, blood pressure. So blood pressure, if it's a continuous feature, I may split it into buckets, or I may use a continuous approximation of the blood pressure. Your homework has an exercise that asks you to do this. To estimate naive Bayes. You can bucket a continuous variable like blood pressure, right? The value could be something you estimate. You say, well, I can have 10 buckets or something, and say my blood pressure is from mean to max, and I can count in data how many times I've seen each bucket. Remember, it's separate for each class. So if I have sick versus not sick patients, I have to build a naive Bayes model for the sick people and a different naive Bayes model for the healthy people. Right? If I have 3 classes, so I have 3 naive. That part is the same like in here. But this, I can either bucketize and count directly. For categorical features, I can do that no problem, right? If, say, it's not a blood pressure, but it's a category. I have a feature that says location or something. I can count how many people are from Boston, how many people are from New York, how many people are from Los Angeles. Or I can estimate it with a very simple model. It could be any sort of model that fits the data, right? Or continuous curve fit. Could be a Gaussian curve or any other curve, but this is unidimensional. Now, I won't insist too much on the naive Bayes. The rest of discussion naive Bayes will happen at office hours. If you run into trouble, this is the kind of thing that just push forward until it works. There's no magic in there, right? It's just, we have to estimate each one of these P. If you have the spam-based data set, there will be 50 probability estimators here, right? One per X, and then the probability of seeing a particular spam, a particular email, or a particular patient is the product of those things. A lot of discussion that you've seen before, probabilities and estimators, if you've seen it in other data classes, applies here. The product is a dangerous thing to do, especially if you estimate the probabilities from data, right? You can easily estimate the zero, like you have no data in a bucket, so you get the zero. Because those buckets are up to us, right? We take the blood pressure values and you divide it in buckets. Some of those buckets will have no data. That's a zero if I use the count as an estimator, right? Zeros might screw up my product here. So what do people do when we estimate frequencies and counts and probabilities directly from data? Log won't help the zero problem. Log helps the computational problem. Instead of getting something with 17 decimals before you get something non-zero, the logs help that decimals, bring them forward. It's more exact computation. So what do people do when I estimate things directly from data? Smoothing. Right? So I don't want to use the frequency as it is, zero by the total or true by the total. There's all kinds of smoothing estimates. We're going to do some of them. There's the simpler ones that you might have seen already, and there's some very fancy smoothing techniques. That's to allow for better estimates, like smoother curves, but also to avoid the zero or singular problems, or even typical very high counts, unusual high counts. So like changing those estimates, but it's still the basic principle. It's a frequency count from data. So I'm going to leave all that, including some of the smoothing stuff, for you hitting the problem set 4 and say, okay, why is my stuff not working? So I want to go back to here. What is the plan here? The plan here, what we're going to call GDA, there's a lot more tables here today. Usually we don't have that many, right? So this shape assumption, let's say GDA, Gaussian discriminant analysis. What we want to do is to say, conceptually, my data, it's plus and minus. So I have a binary classification problem. This is the plus side, this is the minus side. And I have a bunch of points here. These are, let's say, pluses. Occasionally, I may get some minus. And I have a bunch of minuses here. What is this technique here saying? Build a class for the plus side, build a probabilistic model for the minus side. So now, G stands for Gaussian. That means my shape assumption is to be a normal distribution. So I'm going to say, I look at these points only on the plus side, and I say I want to fit a Gaussian curve to them. Now, in probabilities, what do I mean by fitting a curve? Fit a probabilistic model. I know I've said this, and I know you guys know it already. What I mean is, look at the possible values. That is the X's, right? The patients. Patients or images or emails are already featurized for us. Later on this course, we're going to get actual images and emails, and we say, okay, we need to extract features. But for now, you guys have the features already extracted, right? The spam-based data came with the feature, the wine data came with the feature, the housing data came with the features. You don't have to worry where those features are coming from. Extract this somehow from data. The possible data values are X. These are the frequencies, or the chance of seeing that X, right? Because the frequencies, if I normalize them, I get the chance of seeing the X. Fitting a curve to data means I know I've seen this point here, maybe I've seen another one just identical to that, but in reality it's very unlikely to see exactly identical, to see the same patient like down to the very single last value exactly the same. But it's quite common to see similar things, right? So I've seen a bunch of things here, I've seen something here, I've seen something here. This is my data points. Data points are on the x-axis, like where are they? This is a conceptual axis. In reality, there's 50 axes in here if I have 50 features, right? This is gonna measure how many of that data points you see, or what the likelihood is. So if I have a lot of them, I wanna put a big value. It says nothing here. There's another, there's a bunch of them here. I have a value there. So this might in reality be like it's small, has a spike in here, and small again, then a spike in here, small again, spike in here. That might be my data. If I have patients, there is that sort of patient, that's a bunch of people sick that way, and there's values corresponding to a certain blood pressure and a certain other diseases and combination. They don't exist. Patients like that are almost zero frequencies because there's no patient like this. And then there is a very typical patient. This is the people who have flu in January, right? There's a lot of them. And then there's no patient that has a certain temperature and something else, So in reality, this is hard to fit a mathematical model to it if you think of it in a multidimensional sense, right? Like the good thing here is that we modeling or we estimating each feature separately. So if I only put the blood pressure or the temperature, I'm going to look at, okay, what is the temperature range from here to here? And there's probably, most people have no fever, right? That's a spike in the middle. And some people have a little bit of fever, And then the lower than the standard temperature, body temperature 37 is extremely unlikely, right? Low temperature usually means people are dead, right? So that doesn't happen. So for one feature, you can see how the curve is smooth. But if I put all the features here, multidimensional features, there's all kinds of spikes in the data where there's typical points where I have patients or emails, and then the rest of it is pretty flat down. That's the massive disadvantage of this model. In reality, this surface of, here's all the possibilities of the patients, and here are the spikes corresponding to where the data is. The more you see data points like this, there's a spike in there of like indicating frequency. It's very unlikely to be a smooth mathematical curve if I have 50 dimensions. But that's what we want to do here. So in here we're going to say, we're going to assume the data is in such a way that this looks nice mathematically. Again, in principle, I know why it cannot possibly look nice. It's the same brute force estimation problem that we talked about 2 weeks ago. If you look at that joint table, most of the cells will be zero because they are unlikely combinations of people, temperatures, bodies, age, and so on and so forth. So there's no patient like that. A zero in a cell corresponds to some cell, some X patient that there's no data for it. Therefore, the frequency curve is flat. So even though we know this doesn't really work well, models the data, that's the plan in here. So if I make a Gaussian assumption, this whole thing is going to be a nice belt, right? So we draw it in 3D, so to speak. I'm going to have some sort of want to fit a Gaussian to it. This is a 3D Gaussian. So the base of it is like a two-dimensional or d-dimensional thing where the data is, and the height of it is, again, how likely is the data to be there. Gaussians have only one spike, right? So Gaussian form is one spike, and a natural decline on both sides, which is symmetric. Natural symmetric decline. What is the formula? I think we had this before yesterday, last time. Multidimensional Gaussians, probability of X, I'm going to add some things here, is 1 over square root of 2 pi at the power d, I think. That's the number of dimensions, right? And then there is here square root of the determinant of sigma, and there is an exponential of -1/2 x minus mu sigma minus 1. I mean, how which one is transposed and which one is not transposed depends on how it's set up. If this is d by d, this has to be 1 by d. So if I set the vectors 1 by d, I need it this way. If I set the vectors d by 1, I'm going to have to transpose it here. So some of the nodes I have to transpose in here. Okay. So I think everybody can see how this generalizes the unidimensional Gaussian formula, right? We had in here x minus mu squared, right, in the unidimensional Gaussian. Ends up to remember the unidimensional Gaussian formula, normal formula. Okay, 2 hands. Okay, let's write it up. What is this in 1 dimension? The Gaussian formula. We actually just make d equal 1, right? So square root of 2 pi, the sigma becomes sigma, right? It's a 1 value, so that's the determinant, but this is just 1 value. The exponential is of -1/2 x minus mu squared divided by sigma, right? Sigma squared. I think that's the one, right? It's correct? So this curve, everybody knows corresponds to the Gaussian 1 dimension, right? This is the x and this is the p of x. And where's the mean? The mean is here. There is this age range. This is the mean. And what's the variance? It's how spread the thing is. The variance is how open is it here. The more spiky it is, that means the smaller the value. Same thing applies in multi-dimension, but the basis of this is all these possibilities of x, which is a multi-dimensional vector now. If I have the span-based data set, this will be 50 dimensions. So mu, it's got to be a vector, right? This is a vector here that has the same dimensionality as x. If those are 50-dimensional points, their average is also 50-dimensional points. In fact, who's the average? There's mu is going to be sum over all the data points of that vector. This is a vector, right? Divided by. So the sum, vectorial sum, works by components, right? So that's the same as saying, you know, average the first component, the second component, third component. That's going to give me the average. This is a vector. So this is really mu1, mu2, up to mu d, where every one of these mu's is the average of that column. Mu3 is the average of the third column. So I think that's easy to swallow, right? If you understand this formula, that one's not too bad. But how about from this sigma to this sigma? Right? This is a 1 value. Sigma square is the variance, and sigma without square is standard deviation. Right? Their measurement of how far away on average points are to the mean. Right? We know there's an empirical formula for variance, right? So empirical variance, who's sigma square? Empirical. If I have points, who's sigma square? How do I compute or estimate variance from data? So first of all, non-empirical, who's the definition of variance? What's the expected value of x minus mu square, right? Is that it? So that's the definition, but now if I have data, I give you 100 points, unidimensional points, ages in this class. How do you measure variance? Estimate variance.
the sum for each data point, the sum of that data point minus X bar, the average data.
Say mu. Mu would be the estimate. Mu is sum over x divided by n, right?
Yep.
So that I get that estimate. I'm going to put estimates to be clear which one is estimated from data and which one is the actual definition. Right? So this is the mu bar estimate. Is what did you say? It's x minus mu?
Yeah. Squared divided by n.
Right?
A divided by n minus 1.
There's a little thingy with that n versus n minus 1. This is the normal estimator, because if you look at this formula, what you have, expected value of the distance to the mean squared. So if you have a bunch of data points, what do? You take the distance to the mean squared, and then you average. Average corresponds to the expectation, right? It turns out this is not an unbiased estimator. What unbiased means is that if you run it over many times, on average, it's a little higher than the actual variance on average. So the actual unbiased estimator is to divide with n minus 1. There's some mathematics that goes in there. You know, instead of dividing by n, divide with n minus 1 to get an estimate that on average is about the variance. We don't need to worry about that math for now. I want to point out that this is not a problem in data science. This is a mathematical issue, n versus n minus 1. Why is that? In data science, what is n?
Huge.
Not necessarily huge, but it could be 4,000, right? Like 4,000 spam emails, so it could be 50,000, right? Even in the wine data set that's small, very small, I still have n equal 200. So then between 200 and 201, or 199 and minus 1, it won't make that much of a difference as compared to the error I'm getting in the measurements here. Because these measurements will be more inexact than the difference between the n and minus 1. So if you have a real data set, this idea with the unbiased estimator for variance that will be divided by n minus 1 is not that big of a deal. This would be a problem in mathematics if you have n equal 5, that you roll a die 5 times and then you need to compute the variance. Then for 5 versus 4 versus 6, that's actually changing the results. But in data science, if n is at 3,000 versus 2,999 won't be a difference. Okay, so we understand this. What about in the multidimensional case? If I want to do the same thing, we already said the vector is this one with the bar, right? That's the estimator of the mean. What I mean by estimator is that I'm not sure if I get a bunch of data points, the mean is exactly the average, right? I mean, the actual average may be slightly off. So somehow my data points are a little biased towards one side or the other. So there's a difference between the true average and my estimated average. How about this variance thing? If I am to estimate sigma, what would that be? If I apply the same mechanism like in here, what should I get?
The sum for every data point.
So I'm going to make a difference when I work with sigmas and sums, so I don't get confused. This with these dots in here, that's the sigma matrix. And when I draw this without the dots, that's a sum symbol. Otherwise, we might get confused about which one is a sum and which one is a sigma. Okay, so that's, you say from I equal 1 to n, and I can average write 1 over n in the front of it. And what do I do inside?
X minus mu times x minus v transpose.
Again, where the transposes go depends how do I define my vectors. What is the result? It's a matrix what size?
The outer product.
D by
That's
D. So that's got to be D by D. I have to have the dimensions the right way, because if I do D by 1, this has to be D by 1, and this has to be 1 by D. If I do it the other way, I get a 1 by 1 matrix. That's no good. So it depends how you set the vectors. if this is a column vector, makes sense. But if in our notation, this was row vectors, right? Every x was a row with columns. So if I use my notation, it's gonna be transposed in here. So that makes sense that this is kind of like the generalization of this. Like x minus mu squared becomes n minus mu times x minus mu, kind of it looks like that, right? Right. So that is the empirical covariance. Okay, so let me erase this a little bit here. This one we won't need. So the plan is to build this model for y equal plus side, and then to build another model for y equal minus side. So then I'm going to have another, maybe this one looks different, this Gaussian, different than that one. I'm going to fit one Gaussian to that set and one Gaussian to this set. That's to get me those two models in here that I need. If I have two, if I have 5 classes, I'm going to fit 5 Gaussians. And then once I have those, I can do the predictions again by computing all of them, see what gives me high probability. How do I fit a model? So I want a Gaussian that fits the data. Like I explained in here, you can have a high expectation of that process in multidimensional data simply because this actual surface is actually very bumpy. There's no smooth mathematical function that fits it. So why do this? Well, we got to do something, right? So what are our options here? If we want a generative model, we either have to make a shape assumption, aka fitting Gaussians to data that doesn't really fit. But no smooth mathematical function fits, whether you use a beta distribution, exponential, Poisson, whatever. They're all nice smooth function. Look at this. Nothing's going to fit, right? Or I could do the other option, which is make an independence assumption. Also doesn't hold in reality. Right? And estimate this by frequency. Now, remember that even if I estimate with frequencies, I may have this smoothing problem. Some of these buckets in the blood pressure or age might be empty. So if I put a 0 in there, that may complicate my life because I have not enough data to fit every single bucket of every single feature. So I got to do one of those. And later on, perhaps next week, we're going to talk about the way to combine those two ideas. To say, okay, I want independence, but not across the whole set of features. And once I break them into parts, I'm going to try to do a modeling estimator for those parts, which are multidimensional. If I break it into, say, x1 and x2, x3 go together, I still have to fit a Gaussian to those 3 features. But because there's only 3 features, I won't have a surface so bumpy. I have a hope of fitting something nice and round in there. Okay, so back to this. What does fitting mean? So you guys know that this P of x now, it's called the normal of the parameters which are mu and sigma, right? That's a Gaussian distribution. So fitting means find the mu and sigma.
Can we just use estimates?
Right, that's what would make sense, right? But how do we quantify that it fits? What does it mean to fit? I mean, we can use those estimates. So I can fit multiple Gaussians in here, right? Which one is the one that fits the best? Somebody else. So what do I mean by fitting the best?
They maximize the likelihood.
All right, that's the one. So fitting the best Gaussian means the one that maximizes the likelihood. So which one is that? Let me erase this part. I'm going to keep. So the best fit P of X means maximize likelihood. Okay? So say I have two classes, y equals 0, y equals 1. I'm going to follow the notation from here. It doesn't matter if it's 0 or minus 1. Those, which one, the red, blue, sig not sig, 0, 1 means the same thing. And I say probability of x given class y equals 0. Again, follow my notation here. It's going to be 2 pi d sigma sigma 0, this is a sigma 1.
You have to take the determinant of the sigmas and square root.
Let's see. That seems like a complication here, right? How do I actually, first let me write the likelihood down. I want to point out that I could have a further assumption. Let me write it here. Stronger assumption. Is share parameters. For example, sigma 1 is the same as sigma 0. I could say, I could allow different means. Where is the mu 0 here? Or mu, this is y equal, say, plus or 1. And this is y equal minus or 0. The mean is going to be in the middle, right? That's going to be mu 0, average of this data point. And the mean here is going to be mu 1, average of these data points, right in the middle over there. What this model is saying, stronger assumption, the two variances are the same. I could do it either the same or different. I could estimate separate variances for each class or just one variance. Remember the picture here, very bumpy? My Gaussian is not really going to fit the data if it's a bumpy data set anyway. So it may be that fitting one variance for the entire set, irrespective of the plus minus class, assuming they have the same variance, might be a less troublemaker than fitting two variances, especially if the class is two. So that's something you have to play in the homework with. How do I get the sigma to work? Okay, and then we have a likelihood, right? There's another parameter in here. This is a class prior. You don't have to worry about this. So probability of y is this theta at y, 1 minus theta at 1 minus y. That's the fancy way of saying is theta, sorry, not theta, this is called phi. Phi if y equals 1, and 1 minus phi if y equals 0. So this is a class prior is saying how many data points are sick versus not sick. What proportion of patients are sick? That would be the parameter phi, and what proportion is not. So that's class prior. It's only in the binary case, class prior is a phi versus 1 minus phi, right? Because I have two classes. It's the probability of being one way or the other way. Again, that we don't need to worry about this in here because we estimated directly from the data set. There's no problem unless you have a lot of classes, like 3,000 classes. If you have 2 or 3 or 5 classes, you just count each class, divide by the total. That's the class prior. The rest are the parameters that I have. So those are vectors, those are matrices. So the probability is going to be this, right? This is the formula that says for any x value you put in, remember Gaussians, how they look? Again, I erased that. This is the x values, and this is the probability of x, right? Gaussians look like this. So for any x, even x's that I don't have in my data set, right? Gaussians or mathematical models in general can produce a probability for any set of possibilities, right? Even if I put a blood pressure and age and shoe size and whatever that's not in my data set, the Gaussian is going to give me a probability for that, right? Because he can compute, you can put in any value and you get the probability. And how you do it? You apply this formula, right? Once you have the Gaussian, which means what? Who controls this? Mu and sigma. Once you have the mu and sigma, you can put any x, and you're going to get something out of it, right? It doesn't have to be just the data points you have. You can put any x in there. So we want to maximize this. So we want to take derivatives and see what we get. Let's see, so maximize log likelihood will imply phi, I'm going to write the outcome here. Phi is 1 over n, the sum of how many things have y equal 1. There's the proportion of the ones that have the class 1. Mu 0, it's going to be the average of the 0 points, right? So how do we write that down? The sum of everybody who has y equals 0 times, so this is a predicate that says it's 1 when that happens and 0 when it doesn't, times x divided by y equals 0, right? Is that correct? Is it averaging here the points that have y equals 0? I'm saying average the points that have the y equals 0, divide by how many there are, right? So this is the average of x's that have y equals 0. And mu1 is going to be the sum over y equal 1 times x divided by y equal 1. That's the average of y equal 1 of x. And then the variance, it's going to be that formula in there. If I have only 1, I could do separate variances. Let's say for now I'm going to just do 1, which is 1 over n, sum over all data points, x minus mu. What mu? If I have to estimate, we said we have to put a transpose somewhere in here. But if I'm to estimate one variance matrix, not separate variance matrices, what mu should I use? You understand what I'm doing? I'm trying to, I hope it's clear that if I estimate two variances, sigma 0 and sigma 1, for sigma 0 I'm going to use mu 0, and for sigma 1 I'm going to use mu 1. Right? Because it's in here is the average distance from mu 1 to the point, and here's the average distance from mu 0 to this point, which could be different. It could be that these points are very tight about mu 0, and these minuses are far more spread. So it's possible that the variance in the minus world is different than the variance in the plus world. But if I want to do just one variance, what should I do about these mu's? So I figure out the mu that's in here. I don't think that's a good idea, because this mu could potentially be very far away from both classes, while actual each mu is very, like if you look at the variance conceptually, this could be a tight class in here, this could be a tight class in here, yet everyone is far away from where the global average means. So what I have here in the notes, it says you gotta use the mu for that x. So that's xi, right? So who's the mu of that x? Let's put y on y. So if for each x, if x is a positive one, I use the positive mu, and if it's a negative or 0 label, I use that negative mu. So I sum it up over all. I still measure the average to the mean, but for those points I use this mean, and for these points I use that mean to get the sense of variance. So now to his comment, everybody, I think, sorry, you have a question?
Yeah, so you're saying if the x's represent the positive, you take the positive.
So I'm saying this is a empirical, it's an estimate of variance anyway, right? It's an empirical. So you sum up over all the data points. For every point that has a label plus or 1, I use that mu. And for every point that has the label 0 or negative, I use the other mu. I use, when I take this difference here, I don't mean I'm changing the theory. I'm saying when I compute this formula, I know for each x which y is it, which class is it. So I use that class to measure the difference between x and the average. I'm not using this global mu. Because again, they might be tied to the means. That's a good Gaussian case when the classes are relatively close to the mean. Because if it's relatively close to the mean, remember that picture I had in here? Suppose I have a spike like this. Like it's hard to estimate, right? Suppose. What does it mean close to the mean? It means all these spikes are actually close together, right? So my Gaussian is going to come and say, well, I'm going to do this. Because I can't feed every single one of your spikes. So I'm going to, but if this is stuffed together, close together, my Gaussian is still going to be okay, right? So what I'm saying is, imagine if I fit, here's the spikes, and I fit this Gaussian over them. It's not too bad, right? Imagine if I have now a spike here, spike here, spike here, spike here, and I still fit a flat Gaussian, right? This one's be like that. That's not going to work very well because it's too much stuff between the spikes. The difference between this distribution and this Gaussian is quite large, but the difference here is reasonable. Especially, remember I'm doing this for classification purposes. So as long as the one that has the higher probability ends up being the correct one, even if the probability is massively wrong, right? So the probability in here might be correct when it's in this spike, but if I'm in here, the probability is still going to be high, although the actual frequency in the data is 0. Still might be okay for predicting the right class. Because what happens if it's 0 here means I have no data point like this, right? That means if there's no data point like this, maybe I'm not going to get a data point like this in a test set, right? So I won't have to apply these Gaussians. Even though the Gaussian is very wrong in this range here, because that's the reality is that there is no data point that has these particular X features. My Gaussian says, no, there's quite a decent probability to see that. That's wrong. But in the test set, I won't get a point like this, right? Because patients like this don't exist. So I'll get a patient like this. And in here, I'm going to compute the plus side, and I'm going to compute the minus side. As long as the correct side has the higher probability, I'm going to make the correct prediction, even though the probabilities are not real probabilities to count on. All right. So what do we have now? We have the model. Everybody sees how those models work? Fit a curve here that maps the distribution. Fit a curve here that maps the distribution. I would like you guys to think of this independent of the labels. When you fit a probability density function to data, you fit it to a subset of the data points. You don't look at the labels. Like the general process of fitting data, it says take the points and fit a curve through them, fit a probability curve through them, or PDF, density function. Whether I take the plus or the minus separately or all together or some subset of them, the process, mathematical process of fitting data to that set of points is the same process. And it comes down to computing the parameters that give you the maximum likelihood. Likelihood being the product of the probabilities that result from that curve with the parameters you have. So it's asking what is the best mu0, mu1, sigma 0, sigma 1, or like we said, maybe replace this with just 1 sigma to have one variance. What is the best mu0, mu1, and sigma to maximize this? And somebody already said these are the best mu0, mu1, and sigma, right? Right? Is that true? Is this the best? I mean, these are the estimators that we are used to them so far, right? We know that if you want to estimate the mean, that's the mean. If you want to estimate the sigma, that's the sigma. But is it really those values that maximize that formula? Like, if I take derivatives and I play with those things, do I get this or not? Well, let's see. That's going to be a little complicated here. But let's see if we can get stuff out. Before we do so, we said already what we want here. I'm going to connect my computer at the end to show you some plots in here. I have a piece of paper that I wanted to print, and I didn't print it right. So I have a derivation here, which I think we have to work out through it. So apparently class is being canceled, but not this one. Some other classes. We didn't get the you guys didn't get the storm early enough to cancel the class. I don't know. I only seen the header, Tuesday night classes canceled. I guess not, because in Boston they take the snow out quickly. All right, so I have a derivation here which I'm not sure it works, so we're gonna have to work on this together. What we want is the derivative of the log likelihood with respect to mu, right, to be 0 implies mu is 1 over n sum over xi. Again, I'm not going to separate, I'm not going to worry about y plus and 1 minus right now because like I said, I'm just fitting it to some set of points. So let's say the plus side or the minus side or all together. How do you fit the curve to those points? I'm going to leave this as an exercise because that's easy. How do we get the mean to be exactly that? And we need to work on the variance. Let's see. What's this log like? What do I have in here? So now this is not required for this class, neither for grad students nor for the undergraduate people. It's just an exercise, a pure mathematical exercise. It's quite useful if you get in the PhD realm. Like if you get a PhD student, you need what Kitchen did for the neural network, take that maximum likelihood, be able to differentiate it. Same thing in here, how to work it out. But it's not at all required for the class homework exam, nothing like this. Let's see if we can work it out. Is that true? So what happens if I take this log? I take the log of this formula, right? The log of a product becomes a sum of the logs. Log of the probability. Let's look at the probability because the probabilities are going to be replaced with the model probabilities. So log of blah, 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 there's a constant that goes in there. I didn't write the 2 pi, square root of 2 pi, that's a constant. I got a d there, minus d by 2, where is that coming from? Is this d by 2 from the square root, right? Then I got sigma here. Right, but d by 2 is, right, d by 2 is in front of the log sigma, so I think the 2 in here applies to the sigma, right? Because d by 2, if I move it inside the log, I get sigma at power d divided by 2, right? These bars, what does this bar mean? Determinant, right? So the d by 2 is the d by 2 in here, that's right there. Exponential, I take the log of exponential. I don't have nothing, right? Because the logarithm and exponential, they cancel out. And then the inside formula here, I get the -1/2 x minus mu, sigma minus 1. This guy moved a little bit, so I moved the sigma minus 1 outside, right? But then the rest is the same. What I added was the trace of something, right? So I replaced this formula with the trace of.
It's actually, no, that's sum.
Right, so the sum,
So is that this sigma inverse times a sum?
yes.
Okay.
We're trying to figure out where the stuff is coming from. Did I get it correctly? Right. So let's see what we can explain out of this formula. I think we understand that the product in the likelihood becomes a sum. So this product becomes this sum right here, right? Is that true? Because the sigma is the same for everybody, it's a common factor, and the product over the likelihood becomes the sum. This part in here is the beginning of this, so that's out. And then I have the exponential cancels with the log, and then the product that becomes the sum. The only thing I'm adding here is this trace function. Remember the trace function from the differential with regression? What was the trace? Sum of the main diagonal. Can I add the trace in there and say nothing happened? What is this in here? The overall value is what? What dimension it has?
1%.
1. So the trace, no trace, doesn't matter, right? The trace of one element is that element. This is a matrix that's 1 by 1. So I call the trace to the matrix differentials like we've seen in regressions requires an operator like the trace. I even showed you, I think, kind of pushing it. I showed you a general function f, how you differentiate that f with respect to a matrix, and you get a matrix of differentials. But the only function f that we needed at regression was the trace. So what happens here, I put the trace inside to be able to take the differentials. And I can do that because it's only one value. Right? So this matrix is owned by 1. Who's with me? Your hands up so I can see that. Again, it's not required. Okay? We need to do this exercise to verify whether we get this or not. Okay, so assuming we have that, what is the differential? With respect to sigma, right? The log of the determinant is what? Is 1 over, right? So the d by 2, I think that's the log of this is going to be sigma minus 1. So the differential of the log of sigma will be the trace of this. You believe me?
No.
Yeah, we have to see if that's true or not. So my interest here is to give you a sense of how this works. Of course, there's a lot of math details that we can try to work them out, they're gonna take another 3 hours to work them out. But in all the mathematical derivations, there's one thing to understand the main picture, how it goes, and then another thing to go over every detail is truly log of the sigma bar is trace of sigma minus 1. That's a mathematical property that needs to be verified or not. So the way it's written here, I have differentials with respect to differential with respect to mu's and sigma. So this is differential of mu. Okay. So I think in here we need minus sigma minus 1 differential of sigma. That's differential of sigma. And this is differential of sigma. All right. Let's see where this stuff is coming from. I say already log of the determinant, I think, is the trace. Of course, I also have to differentiate. It's like a compound function, so I have to differentiate the sigma, right? So in respect to the sigma differential, that's what I have, if I want the differential with respect to sigma. But if I take the differential with respect to mu's, that's for this part here. Some of the stuff will be differentiated with respect to mu, so now with respect to sigma. Anybody has a clue where this stuff is coming from? Huh? Let's see, what 1 sigma minus 1 is this sigma minus 1 here, right? So how do I differentiate trace of this stuff? Trace, I have trace, 1/2 is 1/2, trace of sigma minus 1, a sum of things. Okay, so how do I differentiate this part with respect to sigma, which is the differential I care about right now? That's a constant with respect to sigma, right? So as far as sigma goes, that's going to be a constant thing. The sum moves out of differential, right? So then I have the differential of the sigma minus 1 times that constant with respect to sigma. There was some formula for the trace, was it? When we did the trace differentials, there was a formula. So what formula I need in here? I have the differential of the trace of a matrix sigma at -1 times a constant. Constant is that sum of x's with respect to sigma. That's what I want. The sigma is in here, sigma minus 1. times a constant. As far as sigma goes, that's a constant. And then I have the differential of the trace operator on it. Is that the stuff in here or not? Somebody's working on it. So let me step back one step. My interest here is not to make you guys mathematicians. If you want to be mathematicians, that's great. But that's not the purpose of this course, right? My interest here is to say, what if you ever want to read a derivation like that in a paper? Not that you want to produce it. Sometimes you need to produce a derivation. That's much harder than to read one that's already produced. So everybody understands that, right? Fine. So how do you read it? How do you go through and say, wait a minute, what is this saying here? It's not a matter of believing it. Suppose we believe it. How do I follow what's going on? You got to keep track first of the main line of the story. Where am I? I have a log likelihood. I'm trying to differentiate it. I'm trying to set it to 0. Fine. And then I have to figure out, once I get the whole story, where are the details coming from? Or if I don't understand the details, where should I go to look for those details? So in here, the problem is that I have a trace formula that I need to differentiate, right? Inside, there's a sigma minus 1 times a constant. The constant seems easy to deal with. It's a matrix, though. This constant is a matrix. And I need the formula for the trace of sigma minus 1 with respect to sigma. Do I have such a formula? I need a formula from the past. So let's leave it like that for now, until somebody finds the formula. I think the formula was in the regression notes.
So, saying the differentiation of trace of AB with respect to A is B transpose.
Right, but this I have differentiation of sigma minus 1 with respect
Yeah.
to sigma.
So that changes.
So I have to find a way to do that. Okay, so that's one step that we need to figure out how that goes. And then I have another step here. That says, I'm going to call this S matrix. Yes.
Wouldn't xi minus mu, if like those two terms, the one up above, wouldn't they be equal to sigma?
So one thing that we have to be clear here, there is a sigma that's a variable, the matrix in my parameter model,
Yeah.
right? And then is this sum here, the empirical variance calculation. So you're saying sigma is going to be equal to that? No.
Not this, not this.
So this stuff in here comes from the main formula, the Gaussian formula. We don't know yet that we're going to obtain sigma equal to that. That's what we're trying to get to, right? So we have a sigma that's a variable matrix. It's a parameter in my Gaussian. And I'm taking the differential with respect to that sigma. And I'm trying to set that differential equals 0. That's the whole story that we had for weeks. What are you saying is that xi minus mu does what?
The multiplication of those two would be equal to sigma, and
But not this sigma.
no.
Because that's what we're trying to get. That's why I'm calling this is a fixed matrix, that's this sum in here. And then when we solve the equation, we want this to be equal to 0, right?
Yeah.
We're gonna find out that sigma is that value. We don't know, I think the confusion here is that we don't know that this sigma is this, the sum that we're looking for. That's what we're trying to prove. Do we have a formula for this sigma minus 1 here? Not yet?
I have one, but I pulled it out of the matrix cookbook. I don't know if it's right.
Well, it has to be this to be right, because that's what we want. Anyway, so assuming we can work that out, I want to follow first the main line of the story here, right? So there's some details about what's the differential of that thing. How do I get NYD minus sigma S? So S is this guy here, right? Is there a common factor between this and this? Right, that's what I'm trying to do here. It's a trace of sigma minus 1 differential at sigma, and then in here I get identity matrix. Identity is because, well, who is this n?
Well, if you multiply by the sigma inverse divided by the derivative of sigma, you get
I get this one, right? Sigma inverse times this sigma, I get this matrix over here. But what about this n here?
That gives you the leftmost component, d over 2 times sigma.
But it's d or n? My note says n, but I think this I need to be d to work it out, to be d. So my point is, I think we can kind of see that there is a trace. The trace distributes over a sum, right? So the trace of that minus that or plus, it's the trace of the. So I have this is a minus, and that is a plus here because it's a minus minus thingy. So that's how I get the minus minus that becomes that plus. I think this is the only thing is why there is a. Oh no, that's a d. So that's d. Correct. That's the number of dimensions, right? So now if I set this to 0,
What happens to the rightmost part of the trace?
this,
Yeah.
I don't know. The rightmost part. So I think what happens here is that I miss a sum. This is sigma minus 1, the matrix, but there is a sum here. What happens, this is 0 because the mean is set up to make the sum equal 0. So if you look at this mean here, this mean, if you plug it in, you get the 0 in there, right? But that's the exercise you have to do. What I said is, if you set up the differential respect to mu to be 0, you necessarily must have this sum equal 0, which means the mu becomes the average of the xi's, which is what's written here. Now, if that mu is the average of the xi, this term goes out when mu satisfies it. So for the differential to be 0, remember the likelihood, like we did for regression, it has to be 0 with respect to all the derivatives, right? Mu and sigma. So to be 0 with respect to mu, that will give this mu and will cancel out this term. That's what I think it happens.
So within this derivative with respect to sigma, we're trying to find the place where the derivative with respect to 0 to sigma is 0, given that we already know that the derivative with respect to mu has to be 0.
Right, because the derivative with mu has to be 0, the derivative with sigma has to be 0. So we can plug in that mu directly that we have. But is it clear where this term is coming from? Where is this term coming from? Here. So how do we get this term? So from here to here, what happened? Hmm? So how do we get from this trace to these two parts? It's another formula that we're going to need. We're going to figure this out. So what do I need to happen here? How do I set this to 0? If I set this to 0, I need, the only way to do this is dID has to be sigma minus 1 s. Which means
So that implies that you know that
this I need to be n, so this got to be the number of data points here. Because if I have this, then the sigma, if I multiply with sigma minus 1, I get sigma and sigma equal s, right? So then I get sigma equal 1 over ns, which is what I want. Okay, so I need to figure out a few things that are question marks. Let's call them exercises. Exercise 1 is this one here. How do I get this derivative to work out, the sigma minus 1? The other exercise is why when I take the trace of this, I get this monster here. What happened from, this is a different part, right? This is not part of this. Is this trace in here? How does this one became this thing in here? So that's exercise 2. The other thing that we have is this n. Where is this n coming from? And I think this is clear, right? To make this 0, I need this to be 0. Well, then NID is that, multiply with sigma, and sigma is s. Sigma will be 1 over ns. That's what we thought from the beginning, right? 1 over n times this matrix is the empirical variance. That's the one we need, right? So is this a complete proof? No. What I figure out is the pipeline in this derivation. I figure out the main line of thinking. I know I have to take derivatives, I get it to 0, I'm supposed to get that sigma underneath. But I still have these details of why is that those 4 things, I don't know where they're coming from. So I don't want to do this again in class. What we're going to do is the people who are math oriented, please come to office hours and show me what you have, and I'll unstack you from there to get all these 4 places written out. You don't need this for this class, but you need it if you want to read a research paper, or even this is a Wikipedia paper as it is, right? To get where the math is coming from. So I know some of you are math oriented. Certainly he's going to try to work this out. Probably some people over here. I think he's going to try to work it out and so on and so forth. But this is not required for the course. All right, I think it's time to go. What is required is we're going to have a new homework. So you guys have the 4 days that I wanted for the neural networks. I don't want to change that. It's the way it is. It's going to be due on, when do you say, Tuesday? The next homework is going to ask you to fit these GDAs. So there's a naive-based problem. How do you fit a GDA? You're not going to need a derivation, right? What you going to do? You're going to compute the mu and sigma directly from these S's, from this formula. I take the empirical covariance, divide by with division by n here. That's going to be the sigma. I have to fit 2 sigmas, or I fit 1 sigma overall. I can compute the means. You know what the difficulty is going to be? There's going to be one difficulty in this one. Here. It's not computing the sigma that's difficult. Sigma, it's very easy. Even if I have 10,000 data points or 10 million data points, this is an easy operation, right? Use also very easy operation, average the points immediately. This is what's going to give you trouble. When you get a test point, you need to compute the probability, right? To compute this probability, everything is going to be nice and smooth up to you get to this sigma minus 1. That's going to be a problem because this sigma is d by d. So if I have 100 features, that's 100 by 100 inverted matrix, right? So my recommendation, strong recommendation, is when you apply this formula, try to use, don't compute it yourself. Your programming language has built in a way to get a normal of d-dimensional, whether it's Python or Java or MATLAB. But even then, you might need to estimate that sigma. What people do, they modify the sigma. They get the sigma with this formula, and then they say, I don't like that sigma, because I can't invert it. Has to do with eigenvalues. We're going to talk about that. So how do I have to modify this sigma to prevent inversions that are very bad? What's the Poor's-Man covariance estimator? Is to up the diagonal. Whatever sigma I have, I look at this diagonal, I say, I don't like small values on the diagonal. Those are the actual variances. Remember when we talked about this, the actual variance? I increase the variances to be at least epsilon, for some epsilon. That's going to prevent an unstable inverse. If the diagonal of the matrix is big enough, the inverse not going to be a hard time. But if you have some elements on the diagonal that are close to 0, the inverse is going to go wild. So you're going to want to use some sort of math help in there, whether you use MATLAB, Mathematica, or some library in Java. That's totally acceptable to not implement that by yourself. So when you get probabilities, you don't get unstable computation. And I'm waiting for the math people to figure these 4 things out. I could try to, I could start, but I can't get a room of a decent size. Just to give back. You can meet one you want. Yes, it's easy to leave, Sunday, like an hour break.
At least two or something. Really?